Hi, this is Paul again. I've got a new video to show you, and this one I'm calling No Chaos 9. In my last video, No Chaos 8, I showed the bDNA going around the second PHI-Rectangle. And what I'm showing in front is the first 120-degree 4-rung section. And the geometry of the rungs came from zigzag vectors. Now all the zigzag vectors all matched up the orientation of the vectors and color of the vectors of the center icosa. I showed in my last video that these 4-rung sections can be copied and rotated 120 degrees about to make a spiral. Now we have another interesting find. We can also give it an additional spiral around this existing spiral. And now you can see we've got something a lot better, because we've gone from 4 rungs to 16 rungs. Isn't that something? And I think this geometry could be used to form a nucleosome, because I've looked at some of the illustrations and this is very similar. So now we don't need the 4-rung system anymore, so we can hide it. Now I think we are looking at a very important piece of geometry. So I think I better show you this going together in stages. So to start with, let's look at them PHI-Rectangles. Now you can see that the purple and green vectors can form a perfect rhombus using the diagonals of them PHI-Rectangles. But for this demo, we only need the green and purple vector as shown. And the purple vector and 3 PHI-Rectangles are gonna be moved up √3 in the vertical axis. And I show a red and yellow vertical vector, and it joins up the 2 ends of the green and purple vector right on the bend. And now I'm going to add 9 green balls and 9 purple balls. And these balls are going to be positioned in perfect order along the PHI-Rectangles. I'm going to use these balls as an alternative to the green and purple vectors. I'm doing this to avoid showing the green and purple long vectors in my next geometry. Okay, now we can move on a little bit. In front we have a vector string of 9 green balls. We also have a string of 9 purple balls. The 9 purple balls are on a higher floor, so you cannot see one of the green balls. Now I'm adding 3 orange balls, and these will be 173 above the purple balls. So now we have the ball framework of the B-type DNA 120-degree section. Now we're going to add colored vector zigzags, and I'm trying to show this task as an easy operation. There's a colored midsection to each of the colored zigzags. So we'll add these midsections in the right sequence between the balls as shown. Now this order took me a long time to get right, so the sequence is very important. Okay, now I'm going to rotate everything around to a better position. And now you can see how them balls are placed better. Now I've made an anim of 7 pairs of vectors for zigzags going into the correct position. I'll reverse it back and I'll do it again. And now you can see that copies of the vectors are coming from the center icosa. And you can see that each of the colored vectors, they are delivered by position only with a locked rotation. So now we have 8 pairs of vectors to go to the purple balls on the top. So now we have a complete set of vectors for the purple balls and the green balls. And now we've just got 1 pair of vectors left. And this pair of vectors are on a higher level again. and they serve as the end of this 120 degree sequence, but it also serves as the beginning of another 120 degree sequence. Okay, by following these instructions, we have saved a lot of work, because there's no need to put every vector in the right rotation in order to give us this string. And now we'll bring it back to the 0, 0, 0 top view. Okay, let's analyze this sequence and see what it's all about. The first job is to hide the swirls and just show a dual helix. Now you can see that the helix goes from the endpoints of the zigzag vectors. Now these zigzags are vectors, they are not rungs. Now if we join the ends of each zigzag vector together, we can then form a center rung. So now we will show the 16 rungs. Now I'm going to make them the same color as the vectors, but don't be fooled, they are not vectors. They cannot be copied from the center icosa the same as the zigzag vectors. Okay, let's give it a little rotation on the x-axis for you to take a better look at this. And I don't think it's looking too bad. So now we can bring back the swirls, and we'll give it a little rotating again to see it with the swirls. And now I'm going to take you to a new scene, because I'd like to focus on the bends of these swirls. First of all, we'll move the bend swirls out of the string. So now what we show are two spagos, spago A and spago B, and the rest of the swirls are all identical. They're 72 degree swirls. I first came up with the word spago in an old video I put out in 2011. It was called DNA Geometry Fundamentals. That is when I found that the sequence rotates 180 degrees on a bend. So it keeps the same sequence, but it's an 180 degree switch. The spago I showed in 2011 was an 120 degree system, and that system only used two pieces. But this system is a 72 degree system, and it definitely uses two spagos, so we use three pieces on this system. Okay, so we'll go back to the 15 swirls again. I've got something else to show you. I've put together an illustration to show how the 15 swirls and angles go together. Every string of 5 72 degree swirls will give us 360 degrees. So we have 15, so that makes 360 degrees 3 times. I think this should make sense to anybody that thinks DNA should come in 3-dimensional order. Now I've got something else to show you also. Now if you looked at my earlier video, DNA Geometry Fundamentals, I showed that each swirl could rotate a bend 3 times. But with the 72 degree swirl, we can rotate the bend angle 5 times. So if you look at this anim, it's very easy to see we can do a lot of things with these bends. Maybe the swirl and the two spagos can be made into a little toy, and then they could put DNA together any way they want. Isn't that something? Just think about it. Maybe the scholars will one day say this is better than the chaos theory. Okay, let's get back to the project. Now the colors are correct on this first 120 degree section. So I've made the colors correct on the second 120 degree section. So now I'll get the colors correct on the last third section. So now I'll put the 3 sections together. Now with something like this, it's easy to make a mistake, but I think this could be done by computer. Okay, I need to add some more sections, but we can't do it on the top view. So let's take it to the front view. Okay, now you can see a 360-degree section. But to make a nucleosome, I think we need another of them sections. Okay, so I think these two sections look very similar to a nucleosome. So let's give it a little spin around. Now I think it's looking okay so far. But in different illustrations, they show that this is linked up to each other. So I'm working on this and I'm going to bring it all out together. Hopefully it's not going to be too mind-boggling. Okay, I've done some research with these 5 rectangles and this is what I've come up with. Now what I'm showing in front of you are 3 nucleosomes strung together. And I've named them A, B and C. Now if you study these 5 rectangle strings, they are all going together in sets of 5 if you look at them. Now when you see one rectangle with another rectangle at an angle on top of each other, that means it's the start of another 120-degree arc. I realize it can be a little bit confusing, but if you hang in, it gets easy. I'll hide the 5 rectangles and just leave the yellow string. I think I'd better tilt the string so that you can see the start and the end. And this makes it a lot simpler to understand. And I think we're looking at something very accurate. Okay, let's go back to the top view again. Now these yellow edges of the string are basically vectors of the icosa. Now I didn't want to color them vectors, so I used colored balls instead. So let's bring them in. Now if you study this geometry, I show 9 balls to each vector, but on the linkage, I show 9 balls going either side of the center ball. So it's easy to see that everything is in a simple order. There's nothing chaos about this stuff. Now we get the rung of DNA between the 2 balls, and I show a helical swirl between 2 rungs. So let's bring the swirls in. I showed earlier on that you only needed 2 spagos and a swirl piece. But when I worked on the linkage, I found that the spago is a mirrored version. So we can call it 3 spagos. So I think we're coming to an end of this stuff in the top view. So now we'll go to the front view for an animation. Okay, it looks simple in the top view, but it looks a lot different in the front view. Let's take a look at it spinning around. Now you can see the way these 5 rectangles go. And you can see that there are 3 sloping segments. Now this is something that should be made with the 3D printer. And younger people can study it to see how it all goes so simple. Now in my earlier videos, I give the dimensions of these 5 rectangles. We are only showing the copies of one 5 rectangle. This is a way of measuring DNA to 10 or 20 decimal places. And it's something very simple and not a complicated highfalutin theory. Okay, let's hide the rectangles and just leave the yellow string. Now I think we're looking at the best way to look at the string. It's kept very simple and it doesn't use so much memory. Now it's easy to see the little step that I've made. It comes between every little sloping edge. And that step I found out is root 3. Now in this anim, we are just showing 3 nucleosomes. So I'm going to make a copy and show 6 nucleosomes. So you can see this thing can keep repeating all the time. You can go as long as you want. I thought I'd better mention also, this stuff is rotating in a vertical center axis. Now this rotational axis is the axis coming from the dodeca set of vectors. And there's 10, 20 of them. I could have shown this as a red and yellow vector going through the center. Anyways, let's go back to the 3 again. And now I'm going to show the balls. When this is rotating in the front view, you can see the sections of balls. There are 9 balls in each section except the linkers, and there are 9 balls from the center ball either side. Now these balls could have been shown as icositas, but they're basically all part of this geometry. I went into all this geometry in detail in my earlier videos. I also showed how the zigzags give the rung geometry for BDNA, so I can't go into all that again. Now I've shown that all this order comes from the vector system. All the chaos theories that ever been taught, there is no mention of this vector system giving you order. Anyways, I've added the swirls to these vectors and balls, and you can see when all this stuff is spinning around, we have a wonderful 3D Platonic order. I think we are just scratching the surface with some of this stuff, and I don't think that 3D geometry should be given the cold shoulder, just to avoid working in 3 dimensions. Anyways, that's enough for today. So this is Paul saying thank you very much for watching my video.